Our title was Simulation of Dielectric Modulation Based Biomedical Application is in Tunneling Device. And okay, so this was the code used, and in this we can see like this is the meshing part we have done. In this, the region has been declared, like there are several regions, like a region for the gate part, a region for the channel part, a region for the oxide part, and several regions, and the dimensions has been mentioned here. The electrode that we have used, that is the gate, source, and the drain, are mentioned here with their dimensions, and here is the doping concentration we have used. And similarly, I'll like go ahead with the this thing demo of the project. So is this visible? My code in the deck build. Is it visible?
Yes, yes, miss.
Okay, okay.
Yes,
So okay, where I am running this right now, and as we can see, like the code, the gate voltage that I have declared is from 0.0 to 3, and in the step of zero point 0.1. So here you can see it's increasing 0.7, zero point 0.8. Similarly, with zero point 0.1 steps, and after that the drain voltage will execute, and then after everything, the structure will be projected, and the graphs that I have obtained, I'll show that. So just a moment, it is almost done. Yeah. So this is the IDVG graph. In this, it is a linear form. So when I convert it into the log scale, it looks like this. And yeah, so this IDVG graph, as we can see, is starting, it has first reverse bias leakage current, that's for this shape. And then after the certain critical gate voltage, it is increasing constantly, not constantly, like exponentially. And after this is the structure. This is the structure you can see, and this is my structure that I have implemented. And when I go to tools and cut line, so just to cut to this channel, we'll see different things that it has to, the different electrical parameter it has to show. So like after this is the doping, this is just the, just a second. So in display where we go, and there is conduction band, and first we'll see the conduction band, energy band. So conduction band I have selected, and I have selected the valence band. So after I apply and okay, so here we can see the conduction band and the valence band. In this code, like we can change the permittivity, and we can import the data from here to Excel, and then we can plot it into the Origin Pro so that the quality of the image is more enhanced and the graph is more looking wise good. So this is the energy band we can see, and similarly there are different parameters. We can see electric field. So I also plot electric field here. So this is the electric field that I'm getting for the permittivity of k is equal to 10 value. Okay, so this is the different, I show you different electrical parameters. So what we have done is, like, every oxide has a fixed electrical permittivity, dielectric constant. So we try to change that, and we try to put our own oxide layer with different permittivity values so that we can observe the reaction, the response the different electrical parameters has to different k value. So in this, we can see like IDVG, the drain current. What we can see is that first, and this is the reverse bias leakage current, and this is after the critical value reached, after increasing potential, we see the spikes. And this is for different Ks like 1, 4, 7, and 10. And we can see that with increase and K values, there is increase in the electric current. So there's like first, if I have to talk about why this type of graph is obtained, it's because of the tunneling of the charge carriers that starts from the conduction band and gets in the valence band. So at zero gate bias voltage, when the band bending arises at the source channel, because of the built-in potential that is present in the source channel, there is this off state, and this off state is where the reverse leakage bias current is observed. And after this, the current is very insignificant, as we can see, it's in the bottom. And in this state, like after we keep increasing the gate voltage is increased, so it will reach a certain state where the minority charge carriers diffuses, and this conduction band and the valence band aligns to each other, and that's when the tunneling happens. So the tunneling charges flow from the source to the drain, And then after that we see the spikes in the this we see the spikes in the current and the like in this we can see how current I depends on several factors. So in this formula we can see that I depends on mu, that is the electron mobility, then C oxide capacitance of the oxide, W by L, that is the width and the length, and this term VGS minus VTH. So this whole term can be described as the K, like the property of the material, that is dielectric. So, like we can't increase VGS and VTH up to a certain limit. Like, we can, of course, increase VGS and VTH, but there is a limit to it will extend. So, increasing the K value is the primary thing that will help in increasing the current in the state. So, like every today, we can see that industry demand high electric and low power consumption. So that we have to change the K value, the material value. So this is what the K value is impacting to the IDVG curve. Now Vibhor will talk about this.
Aditya.
Aditya will talk about the potential and other parameters. Aditya, you can talk about this.
Yes. Next slide, Nikhil.
Yeah.
So, ma'am, like this is
Yeah.
our potential graph which we have compared in three different structures. So, ma'am, like basically we can say that like ma'am by two things like how potential increases. So, ma'am, like we put some biomolecules when in the cavity, ma'am, they have some dielectric constant of their own, like some charge. And ma'am, due to which, ma'am, the electrochemical reaction at the surface and in the cavity, ma'am, occurs, which changes the surface potential of the ma'am channel, due to which the ma'am tunneling occurs. So, ma'am, we can see like as the more potential ma'am increases ma'am with increase in that dielectric constant. And ma'am other form we can say with the formula that V is equals to 1 by 4 pi epsilon naught Q by R, in which 1 by 4 pi epsilon naught is ma'am directly you can say ma'am a dielectric constant. So ma'am we can say that with increase in dielectric constant directly the potential will also increase. Nikhil, next slide.
Okay.
So, ma'am, these are energy band diagrams. So, ma'am, basically, like in basic T-FET structure, ma'am, like where we get a sufficient gate bias, the ma'am band to band tunneling occurs because, ma'am, the conduction band of intrinsic region aligns with the balance band of the P region. What, ma'am, like in comparison, we can see, ma'am, when we increase the dielectric constant, the on current increases, ma'am, and like, ma'am, it is because like when the K bending ma'am source channel bending interface increases, which result in ma'am a reduction of barrier width, ma'am due to which the tunneling occurs and more electrons are formed. So ma'am like we can see ma'am here like in comparison if we can see like ma'am Aditya one's ma'am like structure is good because ma'am like the channel bending is more due to ma'am barrier width reduces and more tunneling is occurred. Next, Nikhil. Ma'am,
So,
Vibhor,
ma'am, in last electric field characteristics, we can see that potential is electric field is directly proportional to the change in potential with respect to lateral distance. Nikhil, next slide. So, ma'am, as the potential increases, the electric field also increases, but it is a negative change of potential. So, ma'am, like this is just opposite graph of the potential. Like the k equal to 10, the potential is maximum. For the same, we have electric field k equal to 10, like electric field is maximum. So this is the and this is the comparison between all the three graphs, and we can see that uh, the electric field is somewhat near, but this red one is higher in all the three. So this is the comparison between all the three. These all characteristics are done. And next slide. For the conclusion, ma'am, like we saw that like in all the four characteristics, like Aditya structure is giving much more better results compared to the like other two things. And this is the Aditya structure, ma'am, which is the best. Like in this we put like he put two gates, and in between that we putting biomolecules. So, ma'am, that's why it's like its structure is performing better as compared to ours. So, this is what is our review about. Like next, and ma'am, like any queries and ma'am, like these references we added, and like
Uh,
next.
Yeah.